Φαίνεται εντάξει?
Ναι, μια χαρά φαίνεται. Οπότε ας ξεκινήσουμε. Καλώς ήρθατε στο σημερινό σεμινάριο. Μαζί μας σήμερα είναι ο Σέργιος ο Αγαπίου, ο οποίος είναι επίκουρος καθηγητής στο Τμήμα Μαθηματικών και Στατιστικής στο Πανεπιστήμιο της Κύπρου. Ο Σέργιος λοιπόν έχει τελειώσει το Τμήμα Εφαρμοσμένων Μαθηματικών και Φυσικών Επιστημών από το Πολυτεχνείο, εδώ στην Αθήνα, το 2009. Μετά συνέχισε στην Αγγλία, στο University of Warwick, όπου έκανε το Master και το διδακτορικό του. Επίσης δούλεψε εκεί σαν μεταδιδακτορικός ερευνητής και από το 2015 εργάζεται στο Πανεπιστήμιο της Κύπρου, αρχικά ως λέκτορας και πλέον ως επίκουρος καθηγητής. Σέργιο, ευχαριστούμε πάρα πολύ που δέχτηκες την πρόσκλησή μας να μας μιλήσει στο σεμινάριο περί Adaptive Rates of Contraction for Spatially Inhomogeneous Unknowns. Οπότε, Σέργιο, μπορείς να ξεκινήσεις.
Ευχαριστώ, Παναγιώτη. Ευχαριστώ για την πρόσκληση και για την εισαγωγή. Να πω ότι η ομιλία θα είναι στα αγγλικά αναγκαστικά για να μην εννοέρχομαι. Απλά επειδή βλέπω μόνο την οθόνη μου, αν υπάρχει οτιδήποτε, παρακαλώ, μπορεί οποιοσδήποτε να πεταχτεί και να με διακόψει, έτσι.
Έγινε, Σέργιο. So, we're going to switch to English.
Okay. Right. So, I work in the setting of function estimation. And I will talk about work done in collaboration with Masumek Dashti and Tabio Helin, and also Sven Wang. So Masumek is in the University of Sussex, Tabio is in La Peranda University in Finland, and Sven Wang is in MIT. Is a postdoc in MIT, and also I will talk about work in progress together with my PhD student Emilia Sava. So this work is found in these three papers. So the first one appeared recently in Bernoulli, and it contains most of the foundations that were necessary for the study that I'm going to describe, and also some of the early results. Together with Sven, we extended some of the results and also considered nonlinear inverse problems. I will not talk in this talk about inverse problems, but just know that they exist. And also with Emilia, we are extending these results to the adaptive setting. Okay, so as I said, I work in the setting of function estimation, and I will start with a motivating discussion for evaluating performance under Besov regularity, and also for using Laplace priors rather than Gaussian, for example. I will then tell you about some classical results on minimax rates under Besov regularity in the white noise model. I will then introduce the priors that I will use, which have tails between Gaussian and Laplace, and I call P exponential. I will briefly discuss concentration of measure results which allow us to study concentration rates of the posterior around an assumed truth underlying the data. And in particular, I will show you rates of contraction under Besov regularity, which I think are quite interesting. For example, because Laplace priors appear to outperform Gaussian priors. Finally, I will show you some preliminary numerics which support the theory. Okay, so we are interested in reconstructing functional unknowns, and many functions exhibit multiscale features. For example, if the unknown is some image, you can see here there are large areas of no action, so constant color, for example. But then there are also areas where there is a lot of fine scale detail, like here, the whiskers of the monkey or whatever this is, or the hair of the girl here. So these multi-scale features should be taken into account in modeling. Okay, so in general in this talk we will be interested in functional unknowns U, which we will assume to be square integrable. And since they are square integrable, we can express them as an expansion in some orthonormal basis psi L, for example, the Fourier basis. Now, Fourier basis functions are global functions, so they are supported on the whole domain of the function, and so they are not very good for capturing localized behaviors. For functions with multi-scale features, it is better to use a wavelet orthonormal basis, which is typically indexed by two indices, K and L, one referring to scale and the other one to location. So here I just show you the wavelets that generate the two-dimensional Haar basis. So yellow corresponds to +1 value and blue to -1. And the basis consists of these compactly supported functions, which are shrinked to smaller and smaller size and also translated around the whole domain. And in this way, this basis can capture localized behavior of the function very well. So given now an orthonormal basis, we can identify a function with its corresponding coefficients and work in sequence space. Okay, so we can work only on the coefficients. So to have a square integrable function, the coefficients need to be square summable. So this is very easy to see. So just to show you, there is this Plancherel identity, which identifies the L2 norm of a function to the sum of the squares of the corresponding coefficients. So the function is in L2 if and only if this norm is finite, which happens if and only if the coefficients are square summable. The idea here is that the faster the decay of the coefficients, the more regular the function in some sense. Okay, so we will measure smoothness using Besov spaces, so what I define here, which we can define using the decay of the coefficients. So you see here I have some norms which are determined by the decay of the coefficients. So there are two parameters playing a role. One is S, and this S is a smoothness parameter. The bigger S is, the faster the decay of the coefficients in order for U to be in this Besov space. And there is also the parameter Q, which appears as the exponent of the coefficient. And this parameter Q determines in what sense we measure smoothness. So Besov spaces are a very broad class of function spaces, and they include many other well-known function spaces as special cases. For example, for Q equals 2, we get the well-known Sobolev-Hilbert spaces. And in that case, S measures the number of square integrable derivatives. For Q equals infinity, and as long as S is non-integer, Besov spaces correspond to Helder spaces, so S measures degrees of continuity of U or even its derivative. Now, we will be more interested in smaller values of Q, so Q less than 2. And for smaller values of Q, Besov spaces are associated with sparsity and also spatial inhomogeneity. So I'm sure you've heard of sparsity before. Maybe you have not heard of spatial inhomogeneity. A spatially inhomogeneous function is a function that is smooth in some areas of its domain and very rough in other areas. Okay, so like the images that I showed you earlier. Okay, so let me try to give you some intuition about why a small q corresponds to sparsity and spatial inhomogeneity in this setting. And I take this from a book draft of Ian Johnstone. So I'm sure you've seen this before, this contour plot of the various LQ norms. So in red are all the two-dimensional vectors which have, say, L2 norm equal to 1. Okay. While in blue here, we have the two-dimensional vectors with L1 norm equal to 1. So a nice interpretation of this plot is that among all vectors which have small L2 norm, the ones which are sparse are the only ones, so the ones which are sparse, these for here, are the only ones that also have small L1 norm. So if I consider vectors with small L1 norm, so inside this rhombus, this diamond here, rather than small L2 norm, what happens is that I exclude all these non-sparse vectors. Okay? And in some sense, I encourage sparsity. Okay? Of course, there are many other vectors that are still non-sparse, but somehow I excluded a large number of non-sparse vectors. So this was about sparsity. Now, regarding spatial inhomogeneity, which is what will play a more active role in this talk. So let's consider this function here, which has two spikes, a sharp one and a less sharp one. Okay. So the function is bounded by a half, so its L1 norm, its L2 norm, or even the L infinity norm are all small. However, we do expect that the norms of the derivative of u will have big values, and this is because of the sharp spike. So the derivative here takes the value of 1 over a. So a, you can imagine a to be quite small, so the derivative is quite large. And here the derivative is 1 over b, so b is a bit bigger, so the derivative is a bit smaller. Okay, so it's reasonable to expect big values of the norms of the derivative. Now, let's see what happens. So the L infinity norm, of the derivative, well, it's just the maximum of the derivative, and the maximum of the derivative is 1 over a. Okay, so it will have a very big value, right, since a is small. Now, the L2 norm of the derivative, well, it will be 1 over a squared, since we need to square the norm, and this needs to be multiplied by the width where it's not 0, so times a, and then plus, sorry, this is the square of the norm, and plus 1 over b squared times b. So in other words, it will be 1 over a plus 1 over b. So again, the L2 norm will be dominated by 1 over a, and so it will be quite large. So it sees the worst spike of the two, and it will be quite large. Now, on the contrary, the L1 norm does not care at all about how sharp the spikes are. So it will be, So it will be 1 over a times a, and 1 over b times b, so it will just be 2. It doesn't matter how sharp the spikes are. The L1 norm will still be 2. Okay? So BS11 norms can be thought of being L1 norms of the S derivative of the function. So according to this intuition, a function with small BS11 norm can have very sharp spikes. Okay. So to take advantage of these properties of Besov spaces, this intuition about Besov spaces, in the context of Bayesian inverse problems, Lassas and Kothos introduced a family of priors, which they call Besov priors, which are Laplace priors, and in a sense penalize these BS11 norm that encourages spatial inhomogeneity and also sparsity. So a very natural way to define priors on functions is to use a series expansion and put a prior on the coefficients. So here we write UL, so the coefficients, we express them as gamma L times xi L. So xi L here are I and D random variables from some density F, and gamma L are some decaying scalings. Okay, and we have the flexibility of choosing the basis, the law of xi L, and the decay of the scaling sequence. For example, the faster than decay of the scaling sequence gamma L, the smoother the random functions defined by the prior. Okay. So BS11 Besov priors are defined by choosing Laplace random variables and these specific scalings. And these specific scalings are chosen so that if we truncate the expansion, we get a prior with density of this form, so it penalizes the BS11 norm of the candidates, let's say. Okay, and since the BS11 norm of a candidate U can be small, even if U is spatially inhomogeneous, this means that this prior allows with non-trivial probability functions that are spatially inhomogeneous. Okay. So here again, S is a smoothness parameter. So the larger S is, the smoother draws are from this Besov prior. Okay, so here you can compare two typical draws from a Gaussian prior and a Laplace prior, so this BS11 prior. So we see that the Gaussian prior has this moderate fluctuation everywhere in the domain, while the Laplace has some areas with little fluctuation and then some rapid change. Okay. So map estimators arising from these Laplace priors have been shown numerically to achieve edge preservation. So in this contribution here. So edge preservation is being able to reconstruct these step type unknowns. While we also recently showed that this idea of, so in this work here, we showed that this idea of penalizing the Besov norm is rigorous in infinite dimensions as well, in the sense that there is an abstract way of defining map estimators in infinite dimensions. And indeed, this abstract way coincides with the penalized least squares estimator with a BS11 Besov penalty. So today we will talk about the P exponential family of priors, which includes both Gaussians and Besov priors. And we will study rates of contraction under Besov regularity of the truth. So before we do that, let's see what is the situation with respect to minimax rates in the white noise model under Besov regularity. Okay, so we assume that we have a direct observation U of the unknown function, a direct observation Y of the unknown function U subject to white noise, which is scaled by 1 over root n. So again, U is the unknown function, but we can work in sequence space as we saw before, so we can work with the coefficients. And given U, we denote by P and U the distribution of the whole path Y. Okay, so the observation is the whole path Y. We are interested in doing asymptotics for recovering the unknown in the small noise limit n goes to infinity. Okay, so consider the minimax risk in L2 loss over a class of unknowns F. And you probably know that this is the best worst case error for unknowns in the class F, optimized over all possible estimators you had. We can then talk about the minimax rate in L2 risk over the class F. Now, we can also restrict only to linear estimators, and then we talk about the linear minimax rate. Okay, now minimax rates in L2 risk for the white noise model and under Besov regularity were studied in the late 90s by Donoho and Johnston. And they showed that for a Besov class of unknowns, so we assume that the unknown is in some space B vita QQ, so vita is the regularity of the unknown and Q is the type of regularity. The minimax rate does not depend on the type of regularity, but only on the smoothness of the unknown, on vita. The interesting feature is that while for Q bigger or equal than 2, linear estimators can achieve the global minimax rate. For Q less than 2, so for unknowns which can be spatially inhomogeneous, linear estimators can only achieve a rate ln which is polynomially slower than the global minimax rate. Okay, and the smaller Q is, the worse the linear minimax rate. So the idea here is that linear methods don't have the flexibility to adapt to both the regular and the irregular parts of the unknown. And we can see this very clearly in this example from this paper of Johnston. So we have this signal. So this is the observation. It comes from nuclear magnetic resonance, and we want to denoise this signal. So perhaps you can see that the signal is, there is an underlying signal that is smooth, but it has some sharp spikes. Okay. But otherwise, in between the sharp spikes, the signal seems to be smooth, but it just has noise. So a good nonlinear method, which is what you see here, and what they use here is wavelet hard thresholding, does a very good job of both removing the noise and also of preserving the peaks, the sharp peaks. On the other hand, a linear method, any linear method, here they use a linear spline smoother. Well, here it keeps the spikes, but it doesn't remove the noise. So because of the lack of flexibility, linear methods can either be tuned to do a good job at recovering the spikes, but then they undersmooth the regular part of the signal and don't remove the noise, or they can be tuned to remove the noise, but then they oversmooth the irregular part and don't recover the sharp peaks. Okay, so I hope it's clear that nonlinear methods do a better job for this type of spatially inhomogeneous signal. Okay, so let's now turn to the priors that we will study. So we take XIL to be an IIND sequence of real random variables with what I call the P exponential distribution. So a distribution with this density. So gamma L are again decaying scaling sequence, and I define the P exponential measure to be the law of this scaled sequence gamma L times Xi L. So P here is between 1 and 2. P corresponds to Laplace, of course, and 2 to Gaussians. And it can be easily checked that P exponential measures are log concave, and this gives some nice properties such as unimodality, existence of exponential moments, etc. So, and again, notice that we define the prior on sequences, but of course we can use series expansions to pass to functions. Okay, so we consider a Bayesian approach to the problem of recovering the unknown function u in the white noise model. And in particular, we put a P exponential prior pi on u, which gives rise to a posterior after observing the data. And we consider the Frequentist scenario that underlying our observations is a fixed ground truth u0. We are interested in studying the concentration rate of the posterior around the tooth in the small noise limit. So this is formally defined in this way, but what you need to keep in mind is we are interested in measuring how quickly the posterior concentrates around U0, around the tooth, as the noise disappears. And we are especially interested in investigating whether Gaussian priors perform better than, say, Laplace for Sobolev tooths. And this may sound reasonable, right? Because Gaussian priors have this L2 structure, which Sobolev spaces also have an L2 structure, so they sound to be compatible. And the other thing we want to investigate is whether Laplace priors perform better for spatially inhomogeneous tools. And again, this sounds reasonable because Laplace priors have this L1 structure, and we saw that Besov spaces with L1 structure encourage spatial inhomogeneity. Okay, so these are the two questions we want to investigate. Okay, so in this business of rates of contraction, there is a very well-known theory developed by Gonzalez and van der Waart, Supraschis, Gonzalez and van der Waart, for studying rates of contraction under general priors and for general direct models. And this theory has two conditions. The first one is that the prior puts enough probability mass around the tooth. And the second, that we can find certain sieve sets which on the one hand capture most of the prior mass, and on the other hand, their elements can be tested against the tooth with sufficiently good type 1 and type 2 errors. Okay. So in the next 3 or 4 slides, I will try to give you a flavor of the tools we developed for verifying these conditions of this general theory of Gonzalez and van der Waart for p exponential priors. Okay. So, associated to a p exponential prior pi, there are two important subspaces. The first one is the space of admissible shifts, which I denote by Q. So, the space of admissible shifts for a measure is the space of translations which produce equivalent measures to the original pi here. Okay, so what I want you to keep here is that Q is a weighted L2 type space, so it's a Hilbert space. Okay. There is a second important subspace for a p exponential measure, which I denote by Z, and what I want you to keep here is that this Z is a weighted LP type space. So it's not a Hilbert space in general for p less than 2. So for non-Gaussian p exponential priors, it's a Banach space, but not a Hilbert space. So it doesn't have an inner product structure. And it is straightforward to check that Z is a subset of Q, and also that both of these spaces have zero measure under pi. And let me quickly show you why this is the case. So if I take the Z norm of my sequence as I defined it, so this is my prior, right? If I take, say, the Z norm, equivalently you can take the Q norm, and I raise it to the power P. So according to this definition, the norm is the sum of gamma L psi L raised to the power P divided by gamma L to the power P, and there is also an absolute value here. So the coefficients cancel out, and we have a sum of IID random variables. And this cannot be finite, right? Because otherwise we will have a contradiction to the strong law of large numbers. Okay, so these spaces Z and Q have zero measure under the prior. Now, in the Gaussian case, so P equals 2 in the Gaussian case, so this Z space becomes equal to Q, so the two spaces collapse to 1, and actually they coincide to the well-known reproducing kernel Hilbert space of a Gaussian measure. But in general, for P less than 2, the two spaces differ, with Z being a Banach space, which is included in Q, which is Hilbert. Okay, now the relevance of the space Z is through this theorem, which gives a lower bound on the loss of probability mass, which we find when moving from centered balls to balls around an element H. So, I mean, the intuition is the same as one dimension. So if I have a log concave distribution and I take the measure of a centered interval, so a centered ball in infinite dimensions, this has the maximum probability compared to taking the measure of an interval in any non-zero center, right? An interval of the same radius. And now this theorem tells us how much mass is lost by passing from centered to non-centered balls. And we see that this mass that is lost is exponential in the Z norm of the center. Okay, so we define what is called a concentration function for a P exponential measure at a point W. And this concentration function, so phi W at epsilon, has two terms. One which involves the prior mass of a centered ball of radius epsilon, so a ball around 0, and a term which involves approximation of W by elements of the Z space. Okay. So in particular, this infimum term disappears for W equals 0. So phi 0, if I'm interested at phi 0, this term disappears, and we just have minus the logarithm of the probability of a centered ball. And from the last theorem, together with approximation, we see that for non-zero W's, the concentration function controls the probability of small balls around any center W in literal L2. So the previous theorem gave us a way to control the probability of non-centered balls, but with a smooth center. The concentration function with this approximation term allows us to do it to control small ball probabilities around any center, even if it's not smooth. Okay, we also have a concentration inequality for P exponential measures, which follows from a nice two-level concentration inequality in U2 Lagrange. And what it says is that even though the spaces Q and Z, I showed you earlier that they have measure 0 under the prior puts most of its mass around a small epsilon shell in L2 around two large balls in Q and Z. Okay, so even though these balls have measure 0, if I take an epsilon enlargement in L2 around them, I get mass that as m goes to infinity, as the radius here goes to infinity, this mass goes to 1. Okay, so the bulk of the mass concentrates in a small epsilon shell around two big balls in these two spaces Q and Z. Okay, so let's return to the van der Waart and Ghosal general rate of contraction theory. And the point of the slides and of this theory that we developed is that we can compute rates of contraction based on this theory of Ghosal and van der Waart by controlling the corresponding concentration function. In particular, what we need to understand is its asymptotic behavior as epsilon goes to 0. Okay, so the ingredients that I showed you, the various results that I showed you, one by one point to the assumptions of this general theory. I will not go into more details in the interest of time, and I will just go straight to the results that we obtained. Okay, so we are going to use p exponential pios with this specific scaling sequence. So tau here is a global scaling, and we will either have it fixed to 1, let's say, or we will let it depend on the lowest level n. Alpha here is a regularity parameter, and indeed one can show that these pios that I define here, they are supported on the spaces B, S, Q, Q for precisely all S which are less than alpha. Okay, and this is why we use the term alpha regular. Okay. Right. So for this alpha regular tau scale p exponential pios, we can find the corresponding spaces Q and Z. Here they are. They are actually, so Q alpha is a Sobolev space, Z alpha is a Besov space with integrability parameter P. And so the concentration function takes this form. And again, what we need to understand is the asymptotic behavior as epsilon goes to 0 if we are interested in computing rates of contraction. So to compute, so to estimate the second term, which is the term that involves centered small ball probabilities, there are some very sharp results due to Frank-Arzada, which show that the asymptotics of the small ball probabilities as epsilon go to 0 only depend on the regularity parameter alpha, and of course on the scaling tau, but they don't depend on p, on the exponent of the prior p. So they don't depend on whether we have a Gaussian or Laplace prior. Now, for the infimum term, there is a standard approximation theory argument that we can use. I say it's standard. I mean, the way of thinking is standard, but the computations, I mean, the computation of this term is what gives the richness of the results that we end up with. But the type of argument is quite standard in approximation theory. So if anyone is interested, I will share my slides later, and this is just the steps of how you approach this infimum. So let's see what rates of contraction we can get using our theory and the Sobolev regularity of the truth. So Sobolev regularity is what we expect that the Gaussian priors will shine. So we'll beat the Laplace priors. So we assume that the truth has Sobolev regularity beta, and we take an alpha regular tau scale p exponential prior, and then we have that the posterior contracts at the global minimax rate in one of the following two situations. So if either the prior regularity exactly matches the regularity of the truth, the Sobolev regularity of the truth, and in that case, we can just fix tau to 1. The second case is if we have any prior regularity alpha, which is bigger than beta minus 1 over p, and we rescale the prior with, so as the noise disappears, we have a carefully chosen rescaling tau. And this rescaling depends on all the parameters in the problem, right? The prior regularity, the truth regularity, and the exponent of the prior p. So to repeat, if the Sobolev regularities of the prior and the unknown match, we get the minimax rate without rescaling and independently of the value of p, while if the regularities of the prior and the unknown do not match, then we need to rescale the prior appropriately, but there is a limit on how undersmoothing the prior can be for scaling to lead to the minimax rate. So an oversmoothing prior can be made as rougher as we need to by scaling, but there is a limit to how much smoother an undersmoothing prior can be made by scaling. So the smaller p's, so here is the regularities of the prior alpha, and here is the regularity of the truth beta. So for Gaussian priors, I can achieve the minimax rate by scaling for alpha bigger than beta minus a half. For Laplace priors, though, I have a bigger window for which I can achieve the minimax rate. Okay, so I achieve it for any prior regularity bigger than beta minus 1. Okay, so we see that perhaps counterintuitively, even for Sobolev truths, Laplace priors in some sense are better than Gaussian because they achieve the minimax rate with rescaling in a bigger window of regularities. Okay, so the same rates, we can achieve them also in an adaptive way. So, for example, we can put a hyperprior on the regularity alpha, so we can use, for example, an exponential hyperprior and fix tau, or we can fix alpha and put an inverse gamma hyperprior on tau, actually on the square of tau. We can also use empirical-based approaches based on maximum marginal likelihood estimation. And we can, again, do this either by fixing alpha and doing it on tau, or by fixing tau and using empirical-based approach on alpha. And this is work done in preparation with Emilia Sava. Now, for Gaussian priors, this has been investigated by Bodon, Szabo, and co-authors. And they took advantage of the fact that the marginal likelihood is also Gaussian in that case. So they could do explicit calculations. In our case, we don't have this nice property of the marginal likelihood, so we need to use an abstract theory that was recently developed by Judith Rousseau and Bodon Szabo. Hey, but it can be done. We show that it can be done. Okay, so let's see what happens for spatially inhomogeneous truths. So we consider a truth which is in a Besov space with Q less than 2, so spatially inhomogeneous truth. And in this case, we can achieve the minimax rate only if we rescale optimally. So we cannot avoid rescaling. And if and only if the prior, has exactly, so the P index of the P exponential prior matches exactly the Q index of the truth. And provided we choose exactly this correct regularity. Okay. So only in this case, based on our calculations, we can achieve the minimax rate. If P is less than Q, for example, if we have Laplace prior, and we have the correct regularity and use rescaling, the same rescaling actually, we can get the minimax rate up to log terms. In all other cases, the rate is polynomially slower than the minimax rate. In particular, for Gaussian priors, the best achievable rate is the linear minimax rate, and we saw that the linear minimax rate is for spatially inhomogeneous functions, it's substantially slower than the global minimax rate. Okay, so we see that appropriately tuned Laplace priors do achieve the minimax rate for basically any Q. So whether we have a spatially inhomogeneous function or even if we have a Sobolev function, while Gaussian priors for spatially inhomogeneous functions appear to be suboptimal. And this suboptimality is not an artifact of our proof. We also have, together with Sven Wang, we have a lower bound which shows that Gaussian priors are really limited by the linear minimax rate. So they are really suboptimal. Okay, so to summarize, for Sobolev tools, Gaussian and Laplace priors have similar performance. For spatially inhomogeneous tools, the Laplace priors outperform Gaussians. And the tuning, which for spatially inhomogeneous tools is a bit more complicated because we need to tune both smoothness and scaling of the prior, can also be performed hierarchically or empirically. And this is work in preparation with my student Emilia. Okay, do I have another 3 minutes to show you a little bit about the numerics?
Yep, sure, Sergio.
Okay, great, thanks. So I will be a little bit quick here. I return to the NMR signal that I showed you earlier, and I will use 2 different cases. One will be I will put a Gaussian prior, and the other one I will put a Laplace prior, alpha regular, tau scaled priors. I will fix alpha to 2 different values, a low one and a high one, and I will put a hyper prior on the scaling parameter tau, and also since this is real data and I don't know the noise level, I will put a hyper prior on the noise precision as well. Okay, and of course for Gaussian priors, sampling the posterior is easier. We have some conditional conjugacy that we can use, and we can just use a Gibbs sampler. There are some complications. We need to use a non-centered Gibbs sampler. I will not go into any details about this. For the Laplace prior, we need to use a metabolism within Gibbs algorithm. Again, we use a non-centered precondition Krag-Nicholson algorithm within Gibbs to sample the Laplace, the posterior arising from the Laplace prior. So there is more work that needs to be done for sampling the posterior in the Laplace case, but let me just show you some preliminary results that we have. So the top row here is for Gaussian priors with low regularity and high regularity, and this is with Laplace prior with low regularity and high regularity. And we see that as in the numerics of Johnstone that I showed you in the beginning, the Laplace prior either does not remove the noise, but reconstruct the peaks, or it removes some of the noise, but the peak is cut short. So if you see here, the peak is cut short. On the other hand, if we use the under-smoothing Laplace prior, it does perhaps an even better job than the smooth Gaussian prior in removing the noise, and it keeps the peak. It reconstructs the peak, the spike well. This picture, I will not give it too much importance, because if I show you the mixing of the chains, of the tau chains, it's horrible for that case, for the Laplace prior. So I'm only showing you this to tell you that there is more work that needs to be done in with the Laplace priors, especially for high regularities, for the sampling of the posterior. Okay, so just to conclude, we have studied rates of contraction with p exponential priors in the white noise model. We saw that Laplace priors outperform Gaussian priors over Besov regularity, and this has tangible consequences on real data. An open question is the sharpness of the rates. Do we really need to tune both the scaling and the regularity of the prior? I will be very happy if I can show that we don't really need to do both, because from an algorithmic point of view, it's it's difficult to tune both, right? The Gibbs sampler is more difficult to mix well if you have to tune both the regularity and the scaling. And in general, for the benefit to be realized with Laplace priors, we need better algorithms, and this is especially if we need to tune both the smoothness and the scaling. So that's all I had. Sorry, I wanted to say that we are also experimenting with heavier tailed priors together with Ismael Castillo. So hopefully this will allow us to get similar results without having to tune the regularity, but only the scaling. This is just a hope. It's very early to say something about this. So that's all I had. Thank you very much for your attention.
Thank you very much, Sergio. Υπάρχουν ερωτήσεις για τον Sergio?
Να κάνω εγώ μια έτσι κάπως απλοϊκή ερώτηση. Στα παραδείγματα που έχεις η Laplace, όπως θα περίμενε κανείς κάπως, λειτουργεί καλύτερα. Υπάρχουν παραδείγματα που σκέφτομαι type 2 error, που η Gaussian να δουλεύει καλύτερα, ας πούμε,
σύμφωνα με αυτά που δείξαμε, τουλάχιστον για αυτού του είδους τα προβλήματα, έτσι, και δεν είμαι σίγουρος τι εννοείς type 2 error εδώ όμως.
Ξέρεις, σκέφτομαι στο μυαλό μου πιο απλά προβλήματα που αν η αλήθεια είναι πιο κοντά στην Gaussian, κερδίζει σε type 2. Δηλαδή... Υπάρχει το ανάλογο, ας πούμε. Δεν είμαι σίγουρος τι σημαίνει όμως το ανάλογο εδώ πέρα.
Ναι. Σε αυτά που κοιτάξαμε εμείς, που προσέξτε, το setting εδώ είναι αρκετά favorable για Gaussian. Δηλαδή, χρησιμοποιώ το loss που χρησιμοποιώ είναι L2, που είναι, κάποιος θα περίμενε ότι είναι tailored για Gaussian, ας πούμε. Ακόμα και για σοπολευτούς που είναι αυτό που περιμένει κάποιος Gaussian να είναι πιο καλά, φαίνεται ότι, όχι απλά φαίνεται, εκτός αν κάναμε κάποιο λάθος, ας πούμε, που ελπίζω ότι δεν κάναμε, φαίνεται ότι τα Laplace priors είναι εξίσου καλά τουλάχιστον για σοπολευτούς, και εάν μιλάμε για spatially inhomogeneous, που εκεί όντως περιμένεις ότι θα έχεις κάποιο πλεονέκτημα με τα Laplace, είναι και καλύτερα εκεί. Τώρα δεν είμαι σίγουρος που πληρώνεις το τίμημα. Ίσως το που πληρώνεις το τίμημα είναι υπολογιστικά, ας πούμε, ότι είναι πολύ πιο ακριβά υπολογιστικά, τουλάχιστον για την ώρα.
Ωραία.
Άλλη ερώτηση? Σέργιο, κάτι είπες πριν για marginal likelihood. Είναι πόσο εύκολο, μάλλον πόσο δύσκολο είναι να εκτιμηθεί εδώ πέρα σε τέτοιου είδους μοντέλα η marginal likelihood?
Κοίταξε, η πραγματικότητα είναι ότι δεν το υλοποιήσαμε ακόμα.
Ναι,
αλλά...
Κάτι ανέφερε σε κάποια στιγμή.
Ναι. Κοίταξε, με Gaussiano μπορείς να γράψεις explicitly, μπορείς να γράψεις κάτω. Βέβαια, όλα αυτά τα μελετάμε στο white noise model, αλλά ο στόχος είναι να χρησιμοποιηθούν στην πράξη σε πιο πολύπλοκα προβλήματα που ούτε τον Gaussiano δεν θα έχει το conjugacy που έχει εδώ. Νομίζω αναγκαστικά θα πρέπει να χρησιμοποιήσεις κάποιο Monte Carlo για να εκτιμήσεις την marginal likelihood. Τώρα, ακριβώς πόσο καλά θα δουλεύει, δεν ξέρω. Γι' αυτός είναι και ο λόγος που, ξέρεις, άμα πας να το δοκιμάσεις, το πρώτο πράγμα που θα δοκιμάσεις είναι να βάλεις hyperprior, έτσι. για μένα τουλάχιστον το empirical base ήταν κατά κάποιο τρόπο σαν ενδιάμεσο βήμα, διότι το πώς λειτουργεί αυτή η θεωρία που χρησιμοποιήσαμε της Judith Rousseau και του Μπότον Ζάπο μελετάνε το empirical base, το rate of contraction για empirical base πρώτα, και μετά έχουν ένα θεώρημα που δείχνει ότι και με hierarchical base πετυχαίνει στο ίδιο rate με το empirical base.
Μάλιστα.
Οπότε, κατά κάποιο τρόπο, εγώ για θεωρητικούς λόγους κοίταξα το empirical base. Αλλά εάν δουλεύει σωστά το Monte Carlo για την εκτίμηση του marginal likelihood, ίσως είναι και υπολογιστικά attractive, με δεδομένα τα προβλήματα που έχει κάποιος στον Gibbs sampler για το hierarchical base.
Ωραία, ενδιαφέρον.
Οπότε είναι λίγο ανοιχτά αυτά τα ερωτήματα. Τα υπολογιστικά ερωτήματα είναι ανοιχτά ακόμα.
Οκ. Αν δεν υπάρχει άλλη ερώτηση, δεν βλέπω άλλη. Να ευχαριστήσουμε πολύ τον Σέργιο.
Εγώ ευχαριστώ ξανά.
Ωραία. Καλή συνέχεια εύχομαι, Σέργιο.
Καλή συνέχεια σε όλους.
Κάποια στιγμή να τα πούμε και από κοντά.
Κοντά, ναι. Σε Greek Stochastics.
Ευχαριστώ. Λοιπόν, καλή συνέχεια, Σέργιο, να είσαι καλά. Καλή συνέχεια.
Γεια, γεια.